So when we talk about potential energy, I like comparing it to gravity because there are a lot of similarities, especially in the equations. Like the force of gravity is always m times g. Now g is actually a lot more complicated. If you remember, Newton's law is actually g times big mass, little mass, all divided by r squared. And so what we did in Physics 1 was we looked at this and we always found that on Earth, this is equal to 9.8. And so really we called this g, and so we simplified it down to m times g, because that's always the case. So the same thing is going to happen here. The electrical field equation is going to be k times the source charge all over r squared, and k is like 8.99 times 10 to the ninth. So we know that this varies sometimes, but the overall idea is the same. Mass will affect the amount of gravitational force. Charge will affect the electrical force. And so when we do potential energy, what we're doing is we're taking the force, and it's basically work. Work is force times a distance. And when we were doing potential energy with gravity, the distance is your height above the ground, your force is m times g, and so potential energy is force times distance. And so that's why potential energy was in joules. It's going to be very, very similar here, except here we're going to just have a distance r. And so if what I do, if I bring this back in here and we replace it, we get q times kq all over r squared times the distance r away from whatever is generating the electrical force. And now this right here was the force, the electrical force, but we're timesing by r, so the potential energy is actually going to be q times k big Q all over just plain r. Whoops, not r squared, just plain r. Now that's potential energy if we have I call this kind of the source charge, and then the amount of charge we're placing in the system. Now, what other people might do is they might decide that, hey, I don't want to commit to putting any kind of amount of charge in that situation. I just want to know basically what is the effect of gravity at that spot. And we're going to talk about that in a moment. That's just called potential. So this is the equation for the potential energy of a system. If you know all the charges, you know all the distances. So first example here. How much potential energy is required to bring two like charges from 3 meters to 1 meter? So the idea is kind of how much energy is required to bridge that gap. See, we're going to have positive charges that are going to start off 3 meters away, and they're going to be repelling each other. So how much energy is required to shorten the distance so that they're closer together? So we're going to look at the change in potential energy. And it's just like in Physics 1. You're going to take the final minus the potential energy of the initial. Now in this case, in both of these, we're going to have k times q squared all over r. Now I write k squared because each of these are going to have a similar positive charge q, and so instead of a capital Q, I replace one of the q's with that. And then for r, I'm actually going to be replacing that with the final distance, which will be 1. Now on the other side, we're still going to have kq squared, except the initial distance is 3 away. And so we can subtract these fractions. This is like 1 over 1 minus 1 over 3. And so we should be coming up with 2/3 kq squared. So one thing to keep in mind here is that this is the total change in potential energy. If you're moving things closer and they want to repel more, there should be added potential energy. As if you were to release that positive charge again, the potential energy would start turning into kinetic energy and they would start to move away from each other. So this is how much is being added to the system probably not best to say how much is required. You would say how much potential energy is added to the system. Okay, so example 2, how much potential energy does it take to bring a charge from far away and place it 2 meters from the other charge? So very similar. We're going to be taking the total change in potential energy, and again we're going to use this final minus initial. Okay, so this is where it's weird. When you see far away, what that basically means is that it's so far away that it had actually no potential energy or no repelling from each other in the first place. So this is kind of the same as if you're thinking about escaping the Earth's gravitation. There is a point where you are so far away from the Earth that the Earth's pull of gravitational pull doesn't actually have an effect. So in mathematics, we just call that infinite. We say that it's just so far away it doesn't matter. So what you do in the equations then is, just like last time, because we have two of the same charges, it's going to be q squared. Now, they want to place it 2 meters from each other, so that's our final. Now, when you're thinking about the initial, we're taking it from far away and bringing it close. And so actually, the radius is going to be about infinite. And if you know anything about this kind of situation, if you take an expression like 1 over n and you let the limit as n goes to infinity of that, you're going to be taking 1 and dividing by larger and larger things, which would be 0. So technically, this is a limit. This is saying, hey, actually, we didn't have any potential energy to begin with. And so the final answer is just going to be this. So there's one thing about potential energy. Electrical forces are a conservative force, just like gravity was. And what that means is, it doesn't matter which path you actually take with an electron. What matters is the beginning and the ending. So kind of like when you were lifting a pile of books, if you were going to be lifting it in the end a distance of x, okay, the work total, or the potential energy, if you thought about it in the right way, is going to be mg times the change in x, the direct change. Now I might carry this book and bring it up and down and up and down and up and down, but as long as you have the same initial state and the same final state, the overall work done on it is just that. So the same with a particle. If I say bringing it close to 2 meters away, I might have a like particle and I might be bringing it all around until I place it here, which is 2 meters away. But it doesn't matter which path I take. And I might even have gotten closer, but as I go back, it kind of gets that overlap gets rid of the work that I've done there. Anyway, if this is the initial and this is the final, those are the only two things you need to worry about.